today I'll be talking about formalizing combinatorial optimization, which is a sub-area of mathematical optimization. Before I would like to just give you a brief, like one-line introduction or one-line definition of what combinatorial optimization is. So it is basically a subfield of mathematical optimization that consists of finding an optimal object from a finite set of objects, right? So you have a set of objects, like for example, like a set of paths or a set of spanning trees or a set of matchings and so on. It's a finite set, and you have a way to map each path or each spanning tree or each matching to some score, and then the goal here of the main problem that is being studied in combinatorial optimization is methods and algorithms to select an optimal object from such a finite set. So as I said, this includes shortest paths, spanning trees, matchings, and flows, and traveling salesmen, and many other problems that are very famous. Here, as Anand talked, I will specifically focus on some recent work that I and collaborators and students have been doing in matchings, but I'll also, but this is generally a bigger effort that we're trying to do. And the main goal here is to build a formal library of graduate and research level results in combinatorial optimization. So we want to have the basic results that would allow you to that will allow you to prove anything that depends on a research that will allow you to formally prove anything that depends on theory that would be existing in a graduate level textbook. And the focus of our work is mainly polynomial time algorithms, because these are the ones that are where there is something mathematically interesting happening. Because if you don't have a polynomial time algorithm, then that means that you're basically just doing a brute force enumeration of all elements in the set, and that's not very interesting from a formalization perspective. So in addition to these textbook results, we're also working on some more modern results in combinatorial optimization that are related to studying new systems, like for example, online markets or online or ride-sharing apps and so on. But in this talk, I will focus on mainly on matching algorithms. So I would like to note before I start that there is a lot of work in formalizing results from combinatorial optimization. So for example, all shortest path algorithms have been already been verified, or their correctness has been formalized by many authors, and I won't list all of them here. Maximum flows has been also considered earlier by Lamich and Sefidgar and Lee as well. And approximation algorithms have been considered. The simplex algorithm for linear programming and integer linear programming has also been done, and algorithms for computing spanning trees. This isn't in any way the first ever try to formalize combinatorial optimization. It is, I would say, though, the first trial to formalize correctness of substantial matching algorithms. So let me tell you what is matching first. Hello? I think there's an echo. But anyway, let me tell you firstly what is matching before I go into this. So if you have an undirected graph like this one, it's a set of vertices, as you can see, and edges connecting them, and between and the goal is to compute a matching of this in this undirected graph. What is a matching? It is a subset of the set of it's a subset of the edges of the graph, and those this subset has to satisfy a specific condition, which is that no two edges are incident on the same vertex. So for example, here the green edges here form a matching because none of them are incident on the same vertex. So this is a matching. And actually, anti-matching is a matching such that there is not any other matching that is bigger than it in size, namely, or in other words, there's not a matching that has more edges than that matching. So that's the maximum probability matching. So Edmonds-Blossom algorithm is an algorithm to compute these matchings for general undirected graphs. So you don't assume anything about the graph other than it's undirected. And the specific goal of that project was to formalize the correctness proof from a book called LEDA, which was published in early 90s, and the last edition was in 1998. And P.S. Lipko and Kurt Milhorn have both contributed to this work in some way or another. So why are we focusing on an algorithm to compute maximum cardinality matching in undirected graphs? So firstly, the algorithm we have considered is Edmonds blossom shrinking algorithm, and that algorithm is very important in the theory of computing because it is the discovery of this algorithm in the 1960s is what inspired computer scientists, and in particular Jack Edmonds, but in general computer scientists, to associate polynomial running time with efficient computation or with effective computation. So this was the first time that this algorithm, discovering it, was indirectly a reason for this association of efficiency of computation and polynomial running time. In addition to that, from a verification perspective and from a formalization perspective, it was a benchmark because it's the second most complicated algorithm in LADA, and in general, it's a really it needs deep graph theory behind it, discrete and discrete mathematics behind this correctness. So it was considered a hard problem for verification and formalization. And Kurt Milhorn, who's an experienced computer scientist, who has tried several times to work on it since the early 2000s, and he considered it to be a many person-year project. So let me just take you through the algorithm. And so, of course, I do not expect you to fully understand the algorithm after this explanation, but I will try and give you a few hints of the following. I'll try to give you a hint of the structure of the algorithm itself. So what does it look like? And a structure of and a few hints about how you prove such an algorithm correct. So what is the mathematical theory behind it? And also what the formalization gave us when we try to formalize these mathematical arguments behind the correctness of the algorithm. Right. So the algorithm is like many other algorithms in combinatorial optimization. So here, this is the top loop. So it's a few loops stacked on one on top of the other. So the top loop is the following: it takes a graph, right, and a matching, and it tries to improve it, right, and keeps improving it until it can no longer be improved. What does it mean to improve the matching? It means to make it bigger, because we're looking for a maximum cardinality matching. So either make this matching bigger or somehow come up with another big matching. So how is this done? This is done by the computation of so-called augmenting paths. So here you have a function that you give it the graph that you're trying to compute a matching for and the current matching, and that function computes this augmenting path. So what is an augmenting path? It's basically a sequence of edges in the graph such that every vertex, such that the first vertex in that path is not in the matching, so nothing has been matched, and the last vertex has not been matched. And another condition on that is that it's alternating. So let me just show you an example here. It's alternating, but and by that I mean edges in this path, every two consecutive edges alternate in terms of membership in the current matching. So let me show you an example here. So this is a graph, and this is a matching for it. Those two green edges are matchings, and this is an augmenting path, right? Why is it? Because the first vertex is not in the matching. So as you can see here, U1 is not touched by any of the green edges, and U6 is the same. It's not in the matching. That's the first condition. The second condition is that an alternating path, which means that every two consecutive edges here alternate in terms of membership in the matching. So for example, this one and that one, this edge is not in the matching, this one is in the matching. This one and that one, this one is in the matching, this one is not in the matching, and so on. So it's alternating. So an augmenting path is an alternating path that starts and ends in three vertices, and as I showed you in this example. Now, if you can find an augmenting path, use that path to make the pre-existing matching bigger by computing the symmetric difference. Again, let me show you the example. So here, for example, we have a matching that has two edges. We computed this augmenting path, and then we make that matching bigger into a matching that has three vertices, three edges, by taking the symmetric difference of the matching and the edges in the augmenting path. The symmetric difference is of two sets is basically the set that contains members of the input of the two given sets, such that each member in the symmetric difference only exists in one of the given two sets. So, for example, here this edge in the symmetric difference because it's only in the augmenting path, but this edge is not in the symmetric difference, it's no longer in the new matching because this edge is in both the augmenting path and the matching. So you compute the symmetric difference between the matching and the augmenting path, and then you compute a matching. And it should be clear that the new matching, or if you think about it for a little bit, the new matching will always be one edge bigger. So that's how you grow your matching. You keep looking for augmenting paths until you no longer find one, and as long as you find augmenting paths, your matching will be bigger by one edge. Okay, so this is the main idea. So the correctness of this algorithm, of this part of the algorithm, the top loop, depends on the fact that being able to prove that if a matching has being able to prove that a matching has maximum cardinality if and only if you cannot find an augmenting path, right? So if you can find an augmenting path, then you can make the matching bigger, and if you cannot find an augmenting path, then there is not a bigger matching. Okay, so this result is actually a result in graph theory from the 1950s. It's called Bear's lemma, and it wasn't necessarily proved for this algorithm, but it is the central argument for the correctness of this algorithm. So for one direction, if you find an augmenting path, you can take that augmenting path with the matching and show that you can always get a bigger matching. And this is really not, although it might need a little bit of thinking if you have never seen this, but it's not very complicated because because the first and the last edges are both not in the original matching. So the first and last edges of the augmenting path are not in the original matching. That means that you will have at least one extra edge after you take the symmetric difference. So this is not a complicated direction. The complicated direction is showing that a matching has maximum cardinality if it has no augmenting paths, right? And proving this is not easy at all, at least non-trivial. So how do you prove something like this? So firstly, so I don't want you again to understand the full proof, but I want you to just get a hint of the kind of arguments here, and then see what the formalization helped us with. So the kind of argument is the following. So you say this maximum matching is maximum cardinality, and then you show that if there is, you have this matching, and then you prove that if there's another matching m prime that is bigger than m, then then you can somehow derive an augmenting path. So you show that for any matching m, if there is a matching that is bigger, you can always construct an augmenting path. So how do you do that? The proof is a few steps. The first and most complicated step is the following. If you take the symmetric difference between the original matching m and the bigger matching m prime, you will have a result that is a number of edges will be a result, and those edges form a third graph. So the graph formed by the symmetric difference between the two matchings has the following property. Any connected component in that graph will be either a singleton vertex, an alternating path, which I will repeat again, an alternating path is a sequence of edges that alternate in terms of membership in a given matching. But here what I mean by alternating path here is it's a sequence of edges that alternate in terms of membership of m, or an even alternating cycle. So a cycle that has an even number of edges, right? So this trichotomy of that you have to prove for the connected components is actually not is a long, complicated proof if you try to formalize it. And then you do a few other steps, but I won't go into those steps because I think it will be hard if we don't have like a whiteboard or something to show you the meaning of the other steps. But the important thing is that this step is rather complicated. So one result of this formalization is that we were able to simply ignore this step by being basically forced to come up with another proof, because proving this this trichotomy was it's really complicated and has many symmetric cases and thousands of lines. So we basically were forced to come up with another proof that quite simply doesn't do this step, and we in fact showed that you don't need this step to prove the theorem. So that's an interesting outcome in my opinion of that formalization. Now this is the top loop of the algorithm. So I will try and give you some more ideas of what was in this Edmonds Blossom algorithm, Blossom shrinking algorithm, and proving it correct. What other ideas there are. So the second step here is actually how do you find an augmenting path, right? Because the top loop assumes that you have a procedure that can find the augmenting path. So this augmenting path search, but how do you actually do that? So the way you do that naively, if you want to do that naively, you can try a version of breadth first search or depth first search, but both of those will not work. For example, if you want to use breadth first search to find an augmenting path, you will modify it and have the so-called alternating breadth first search. So you would do a breadth first search, but you make sure that you only include edges in an alternating way, so in a way that alternates in the matching. But the problem with breadth first search here is that if you have an odd cycle in the graph, so for example here you can do breadth first search. You can go from U1 to U2 and U2 to U3 and U3 to U4 and U4 to U5. With regular breadth first search, you wouldn't go to U3 because you only want to see, you can see only every vertex once in a path. But if you're doing alternating breadth first search to compute an augmenting path, you will need to do the following modification to breadth first search. You will need to make sure that every vertex is only seen once at an odd distance from the root and once at an even distance from the root. So that means that you can that means that you can see U3 twice, because the first time you arrive at U3, it's at an even distance, and the second time you could arrive at it is at an odd distance. And this will just not work. So you cannot use alternating breadth first search. And if you try and do depth first search, you will find a similar counterexample. So there is so this doesn't work. The main insight of Edmonds Blossom algorithm is that before you even look for augmenting paths, you remove all odd cycles, because the problem really here is that we have odd cycles in the graph. So if we remove all of those odd cycles and then do our search, then we avoid the problem that I tried to describe in the slide before. So how does Edmonds Blossom algorithm do that? It simply tries, whenever it finds an odd cycle, it shrinks this odd cycle into just one vertex. So for example, so here it just takes the quotient of the graph over that odd cycle. So you have that new graph. And then of course you have to prove that you have an augmenting path here if and only if you have one there, right? So and this is and you basically want to show that if you remove these odd cycles with this shrinking operation, you're not losing any augmenting paths, and accordingly your algorithm is still complete and has theoretical guarantees. So there are two directions in this proof, as I said, or as I hinted to. The first one will be to show that if you have an augmenting path there, then you can derive an augmenting path there, and the other way around. If you have an augmenting path there, you can derive an augmenting path in the upper graph. And I won't be able to go to the details here, but the proof of that is extremely tedious, and it has a lot of symmetries, and we couldn't do really much about it other than just perhaps derive some lemmas that remove some of the symmetries. But it really showed us that symmetry breaking is something that is not solved in theorem provers as far as we're aware, and especially in Isabelle, where we did that. You have to basically manually design lemmas that make you avoid the symmetries, even though this should be automated somehow. So this is an outcome of this proof. And the last thing is actually, how do you find these odd cycles or augmenting paths? So I will have to just try and give you like a brief hint of how that works, because we don't have the time to go into details. But basically, you do a so-called you build, instead of doing a breadth first search or a depth first search, which both will not work as I showed earlier, you do something else, which is that you construct a forest from all vertices that are not in the matching. So you construct a forest, it's called an alternating path forest, and then use that forest to find paths or blossoms, augmenting paths or blossoms. And what is a blossom? A blossom is just an alternating path that starts from an unmatched vertex and ends in an odd cycle. So either you try and find something like that and then contract this odd cycle, or you find an augmenting path that doesn't have an odd cycle in it. So the algorithm does it has to do one of the two things, right? And the algorithm, in fact, again, does this odd even labeling of vertices based on their distance from the root where you started your search, and it makes sure that every edge is examined only once. So what is the point that I'm trying to explain here, because it's impossible, of course, for me to really explain how the algorithm works other than just giving you these high-level properties. The point that I'm trying to make here is that this is like a very complicated while loop that has two branches, right? And each execution branch is complicated, and it's complicated in its own way. And reasoning about this in a theorem prover is actually very difficult and intimidating. So why? So let me describe that to you. I'm assuming that not everyone here has verified algorithms, so I'll give you, like I tried to summarize to you why it is complicated to reason about such big while loops. So in order for you to prove that this algorithm works, as I said, you have to show that it can either find an odd cycle if one exists, or an augmenting path if one exists. So you need to show that its output will be, like, if it gives you an output, then it's either a proper odd cycle or a proper augmenting path. In order for you to show that, you have to actually show a lot of sub-properties of the output. And then though you have to show those sub-properties, like, for example, that it will give you alternating paths, like the paths computed by it will always be alternating in terms of membership in the matching, and a few other properties. And you have to design those properties so that they imply the main property that you want to prove, which is that the algorithm either gives you an augmenting path or gives you an odd cycle. The second direction, which is the following, which is that if the algorithm does not find anything, then there is not an odd cycle and there is not an augmenting path. And this is based on showing that the algorithm, if it finds nothing, then it can always construct a certificate that no odd cycle and no match and no augmenting path exists. So in order for you to prove something like that about a while loop, you need to specify and prove so-called loop invariants. What is a loop invariant? These are conditions about variables that are preserved, about the variables in a program that are preserved along the loop's execution. So for instance, in our case here, we want to show that as long as we execute this while loop, for instance, I don't know, you will not, if U2 and U1 and U2 will never have been processed before, because you only process fresh edges, and so on. But because this loop is rather complicated, the proof actually needed 18 loop invariants, or needed us to specify and prove 18 loop invariants. So when I say here 18, I don't mean like properties that have nothing, like that are uninteresting, or that are just an artifact of the fact that we're formally proving the algorithm correct. No, these are mathematically meaningful properties, so 18 properties. And like for one like such properties, for example, as I said, like any examined edge has an odd labeled vertex, like for instance, properties like that. And you have to come up with all of these properties, and then you have to make sure that first of all, each one of them is maintained across the loop. So every iteration, you can show that this property is maintained, and then you have to show that combining then give you the properties that you want, the final properties that you want of the whole while loop. So what is the interesting thing that we found in formally proving that this algorithm is correct, or this part of the algorithm is correct, this while loop? The main thing is that this textbook where we started later had only 11 of those invariants, and those are enough only to prove that if the algorithm gives you a path or an odd cycle, then these are sound. These are either a sound path or a sound odd cycle. But it did not have enough invariants to prove that if the algorithm doesn't find anything, then there is not an odd cycle and there is not an augmenting path. And this, yeah. So the mistake there was a bit technical, so I won't go into it. But if you're interested in that, just ask me afterwards. So as I said, so the outcomes of this project were, so we found those invariants that were missing, and we found a much shorter proof of Verge's lemma. And indeed, Kurt Milhon, who wrote that book, was saying that the formalization of this, like this formalization, was why he understood the proof, like fully understood the proof of the algorithm. In fact, before that, he didn't understand why, like he didn't understand or didn't think that there is a need for invariants to show that the algorithm will never miss an augmenting path or never miss an odd cycle. So that's the first result I wanted to talk about. The second one is also in the theory of matching, but it is in a different setting. So here we're talking about online bipartite matchings. So we're talking here about bipartite graphs. These are so this is a graph that an undirected graph as well, but that is divided into two parties, and edges only go between those two parties. And when I say online here, what I mean by that is that one side of the graph arrives online. And what does that mean for an algorithm like this? That for an algorithm like this, that means that when such a vertex arrives on the online side, you have to immediately decide if you're going to accept one of its edges in the matching or no. You cannot wait until the entire online side arrives and then decide compute your matching. You have to do it online as edges arrive. And this models a lot of practical situations, like, for example, ride sharing or online markets of different sorts. So to just describe the setting, like here you have an offline side and an online side, and an online side vertices appear one at a time. Each comes with its own associated edges. For example, these edges could be modeling some sort of mutual interest in buying and selling or something like that. So here you have this first vertex. It came with two edges, right? And then once this vertex comes, you have to decide if you want to include any of these edges in the final matching or no. Once the new vertex arrives, you can no longer do anything about the matching. If you included this edge, for instance, then you cannot remove it. And if you didn't include any of the edges, then you cannot add any of them. So the vertices arrive online like that with their edges, and then you have to decide as every vertex arrives. So what we did here was to try to prove like there's an algorithm for solving these online matching problems, solving these online bipartite matching problems, and that algorithm is from 1990 and has been since then generalized in many ways to model many different types of online markets. And I don't mean online as in like on the internet, but I mean online in the sense that buyers and sellers arrive and go as you're trying to solve the problem, and you cannot wait until everyone arrives to start coming up with a solution, because if you do that, then many of them might have lost interest and left. So you have to make a decision online. And it's although it sounds like just as like if on the surface of it, it might sound like we're just talking about a small practicality, but in reality, it makes a difference. If you have to make the decisions online, it makes a difference in how optimal your solution can be. So because you can miss edges, or if you rush into taking an edge that shouldn't be taken, then you could miss a bigger matching, for instance. And the other way around, if you don't take an edge, you could be also missing a bigger matching. So that algorithm is a randomized algorithm. So for the first step of it is that it randomly permutes the offline side of the bipartite graph. So you have here this is like the original, like the offline side is like that. You randomly permute it, and here the random permutation goes from 1 to 6, for instance. And then again, the online vertices arrive, as I said, with their edges. And the algorithm does the following. For every arriving vertex, all what you do is just one thing. You take the edge that is connected to the top free vertex in the neighborhood of that of V1. So for example, here, V1, when it arrives, it has the neighborhood is U3 and U5. And you just take the top edge, the edge connecting to the top free one in this random permutation. And the same for V2, when it arrives, you take the top one, and V3, you take, for example, V3, it's connected to U1, U2, and U4, but the top free one is U2, so that's the edge that you take. So these green edges are the ones that are taken into the online matching. So the algorithm itself is like, it doesn't have much control flow, because it's you just do the random permutation. So there's just top loop that does a random permutation of the offline side. And then once you have that random permutation, you call this other subroutine, which does exactly what I said. So on the slide before, you have the online side, and every vertex that arrives online, you see if it has an unmatched neighbor. Then if it has any unmatched neighbors, then you take the top ranked one, and you go on. You do that for every arriving vertex. So what can you prove for such an online algorithm? So as I said, the fact that we're computing the matching online might mean that you miss edges or add edges while you shouldn't have done that, because they could cause you to miss the maximum, like the maximum probability matching. The output of this algorithm is not necessarily the maximum probability matching, but you can prove about it the following: that the size of the matching computed by ranking is always greater than or equal the size of the maximum probability matching multiplied by 1 minus 1 over e. Of course, this is the expectation, because here ranking is a randomized algorithm that operates based on a random permutation of the offline side. So if you take the expectation over all possible random permutations of the offline side, the output of ranking has to be greater than or equal this fraction of the maximum probability matching. And this is called the competitiveness ratio of the algorithm. And this is, of course, in the limit with respect to the size of the given graph. But so proving this bound has a lot of aspects to it. The first one is the probabilistic aspect, because you're talking about an algorithm that does these random permutations. The second one is the graph theoretic aspect, and the third one is the asymptotic part, because this is in the limit. So I'll briefly talk about the two aspects of the proof: the probabilistic and the graph theoretic one, and we'll not talk about the asymptotic one. So the proof of this algorithm actually is non-trivial, and it has been studied. Just the proof of the same algorithm has been studied at least 5 times since its introduction, and each one of those papers try to simplify the proof in one aspect of the proof. These are all non-formal proofs; these are just pen and paper proofs. And what I and Christoph Madlener, who was a former student of mine, decided to do was to formalize one of the papers, the paper from 2008, which was called Online Bipartite Matching Made Simple. And it claims that it presents a simple combinatorial proof of the algorithm. And here's that proof is what I'm going to show you. And I don't you will be surprised that this actually is not simple. Once you formalize it, you find that there is a lot of things that are missing. So the first part of the algorithm, the first part of formalizing the process of such a randomized algorithm is modeling it. So we used in Isabelle, we used the GI monad to model this algorithm. So here you have you draw a random permutation, a uniformly random permutation from the set of all permutations of the offline side. So the offline side, the set of vertices in the offline side is called U, and then you draw a uniformly random permutation like that, and then you call online match, which is the part of the algorithm that just recursively goes through the online side and chooses edges to add to the matching. So, and we used here the J monad, which was developed by Manuel Eberl and Johannes Hölzel a few years ago. So the correctness of this the correctness proof of this algorithm has 2 parts. The first part assumes that the bipartite graph that we're talking about has a perfect matching. What is a perfect matching? And it's a matching that includes all the vertices in the given bipartite graph. So yeah, if you assume that our graph has a perfect matching, can we show that the algorithm has the required competitiveness ratio? And this algorithm, this part of the proof is really just about manipulating probability distributions, and nothing mathematically interesting or surprising was found there. The only thing that might be interesting in this part of the proof is how you reason about distributions in a formal setting and random probability distributions, and also algorithms that are represented as probability distributions. So one lemma, for example, says that if we take xt to denote the probability that the offline vertex of rank t, so in the ranking that we have made, if we take the vertex at position t, the probability and say and wanted to say what is the probability that this vertex is matched. So xt is the probability that the vertex at position t is matched. Then this probability, 1 minus this probability, is upper bounded by the probability that all vertices of the ranking, all the vertices of a higher ranking, were matched, right? So the point here that I'm trying to show you is just the shape of the goals, or the shape of the things that you're trying to prove. So something like this. So 1 minus xt, where xt is a probability distribution, is more than or equal than this summation. So how do you go about doing that in Isabelle? The first thing is that you model XT, and how do you do that? You just model it as again using a Jerry monad as a randomized experiment. So XT is the probability that the vertex at position T was matched. What does it mean? You firstly draw a you randomly draw sigma, which is just from U, which is uniformly drawn again from all permutations of U, and then you give that sigma to the algorithm that goes through the online vertices and adds edges recursive as it goes through every online vertex, and then you return true if and only if the sigma of T, which here means that the vertex at position T was matched or was a member of the matching computed by ranking. Now, the way you go around proving that, it mirrors really what was in the pen and paper proof. So you have the first distribution, and then you devise a second distribution that makes the proof easier. For example, here we devise a second distribution that removes the dependence between the sigma of T and sigma, which is necessary for the proof, like it's for technical reasons. But the main idea here is that you derive one distribution after another, and then you show some equality between them, or some, like in terms of expectation, some equality between them. And then we derive here a third distribution. So here, that first distribution is what I described earlier, and then you replace the sigma, and then you come up with we devise another distribution that draws a random U, and then instead of saying sigma of T, you give to online match sigma by replacing whatever was in position T with U, and then return U like true if and only if U is in the match in the new matching, and then we come up with another distribution which was also needed for the proof in pen and paper. So all what's interesting here is really just how efficiently can you reason about these distributions in Isabelle in a formal setting. How can you represent them and reason about them? That's what's interesting here, but we didn't find anything mathematically interesting. Now, the second step of the proof is to generalize the guarantee that we just proved. So if you remember, this probabilistic guarantee that I told you in this first step only proves that the algorithm works as expected for bipartite graphs that have a perfect matching, meaning the bipartite graphs for which there is a matching that covers every vertex in the graph, in the bipartite graph. So now we want to generalize that. How do we do that? The idea basically is that you're given a general graph, you remove vertices from that general graph until you reach a subgraph that has a perfect matching. And you do so in a way that guarantees that the subgraph that has a perfect matching, that the perfect matching of the subgraph has the same size of the maximum probability matching of the original graph. It sounds a little convoluted, but you can actually do that. And the basic theorem, or the basic result on which this depends, is the following. So here we have a bipartite matching that I showed you in the example earlier, right? And I will just show you the result that this generalization depends on is the following. If we remove U2 from that graph here, for example, what happens? Like what happens to the output that is computed by ranking, right? So if I remove U2, when V3 arrives, it will no longer it no longer has U2 as a neighbor, so it will be just matched to the next free vertex, which is U4. So here we removed that edge from V3 and to U2 and added the V3 to U4, right? And that means that when V5 arrives, it no longer can match to U4 because U4 is now matched to V3 and it's no longer free, and then it will be matched to U5. And V6 will be matched to no one because U5 is no longer free. So this generalizing the proof from a bipartite graph that has a perfect matching to a bipartite graph that does not have a perfect matching depends on showing that if you remove a vertex, that the matching computed by ranking, so this matching, that the new matching, differs from the old matching with an alternating path. So here, for example, the difference between the two matchings is that this edge was removed and that one was added instead of it, and this one was removed and that one was added, and this one was removed. So as you can see, this path, like the edge, the difference between the two matchings, alternates in terms of membership of the old matching. So here, this path was in the old matching. This was not. This one is. This was not. This one is. So and and this is like, if you try like the proof of this like lemma in the paper was just showing this figure basically, and if you try it, like if you think about it for a minute, you will see actually that it's quite obvious. If you remove a vertex, then the new matching will just cascade down, but all the entire difference between the two matchings will just be an alternating path. Of course, trying to formalize that was much harder than done than said. And it was, in fact, the vast majority of our effort. Like this step that I'm thus describing here is just one line in a 16-page paper. But in the formalization, when we tried to formalize the step, it was almost 65 or 70% of our effort, if I remember correctly, in terms of conceptual effort of coming up with a proof, and also in terms of formalization lines, like lines in the formalization, lines of proof scripts. And for example, one complication is already how do you even discuss this difference, right? Like so discussing this difference can be done with this. We didn't find any better way other than this mutually recursive representation or way to characterize this difference. And then if you want to prove anything about this difference, then of course you have to deal with simultaneous inductions, which are not easy at all to deal with. So the outcome here, again, like Edmonds Blossom algorithm, was that we saw that when you talk about like a graph theoretic, an algorithmic graph theoretic result like that, and try to formalize it, you could be surprised by how complicated it is in comparison to the pen and paper version, where you gloss over many details. So this was mainly the technical content of the talk. So I'm also working with again with students and other collaborators on a few other results from combinatorial optimization and formalizing them. So we're working on algorithms for weighted matching, for instance, which is a generalization of Edmonds' algorithm, and also algorithms for minimum cost flows and for connections between matching and flows and linear programs, as well as algorithms for matroids. And these are basically like, hopefully if these things are done, then we have a lot of these things are done. For example, this algorithms for minimum cost flows were done by one of my current PhD students, Thomas Ammer, and it's currently under review. But when we're done with these things, then we basically have in Isabelle a comprehensive theory of combinatorial optimization that covers almost all the material in any of the graduate level textbooks. So just a few notes on the formalization, also challenges with the formalization, other than what I have stated already. So what I've been talking about really is challenges with the mathematical part of the formalization. So what was difficult about the mathematics of the proofs, but there are things that I didn't talk about, and I will not really have time to talk about, but I will just tell them to you very briefly. So formalizing results like this bring up challenges that you wouldn't really think about until you formalize them. Like, for example, what is the proper graph representation? Like, there are many different types of many different ways of representing graphs. Like, for example, you can have a representation that is geared towards executable algorithms versus mathematical statements. You can have a representation that is geared towards directed and undirected graphs. You can have representations that have an explicit vertices versus not. So this is one thing. Like, deciding, like, one goal of this project is to come up with one representation that can fit all the results, and it's really hard. But the way we're currently doing it is by just writing down adapters between all the different representations that carry the concepts from one representation to the other. Another aspect of also is representing computational objects or algorithms. So the naive way to present algorithms in a theorem prover is functional programs, and this is actually what we have followed throughout our formalizations. It's because the main advantage that it's native to the theorem prover, so you don't need to build any new definitions or anything. You just write a functional program, and you model your algorithm as a functional program, and that's it. But there are, of course, other ways like wild combinators or deeply embedded languages, and each have their own advantages. And the last thing is how you compositionally reason about these algorithms. So when you're talking about an algorithm like what I showed you earlier, if you want to have that algorithm be executable, you have many aspects of its correctness. The first aspects are what I discussed with you, the mathematical background theory behind it, like why is it correct from a graph theoretic perspective or point of view. But then the second aspect is, if you have a certain implementation, you need to show that this implementation is correct. Like, for example, you can model sets as trees or as in other ways of implementing them, and you need to you need to decompose your proofs in a way that separates reasoning about implementations from reasoning about mathematics. So this is also, there are a few ways to do that. So the way we did it was using Isabelle's locales, but there are other ways, like for example, most notably automate like an automated refinement framework by Peter Lamich, but it has a very steep learning curve, and this is the main disadvantage. And another disadvantage is that its proofs written in it are rather opaque, so you have a lot of automation and you don't really know what's going on if you don't know how to debug the tool. But of course, the advantage is that it's less cumbersome than locales if you can use it well. So that's all. Thank you for listening, and I look forward to your questions.
Thanks for the talk. Are there any questions from the online participants? What about from the Cambridge audience? Okay, there's one question over here.
Just on the last slide, you were comparing locales and automated refinement.
Yes.
Yeah. Could you expand on what automated refinement means in this?
Yeah. So automated refinement. So Peter Lamich has developed, like, this is not really like a general concept. It's a specific tool by Peter Lamich that's called, he calls it the refinement framework. But the main idea is the following. Like, if you're like here, what I said is that you're trying to separate the mathematical reasoning from implementations. What does that mean? I will explain it to you in terms of locales, and then we'll tell you what the automated refinement does. So if you're doing this kind of reasoning with locales, what you would do is you would are you aware of what locales are?
Yes.
Yeah. Okay. So if you do this in terms of locales, what you would do is the following. In your locale, you would just fix a placeholder for an implementation of sets, let's say, or maps. So a set can be, if you want to implement a set in a way that is computable, you have to implement it, for example, as a tree or as an array or something else. So if you're doing this with a locale, you just assume that you have an implementation. So you assume you have functions from an implementation, but you don't know how those functions are implemented, and then you do all your proofs like that. And then afterwards, you then instantiate these locale assumptions with an actual implementation, like for example that uses balanced trees or that uses arrays or something else. But like one type of balanced trees, for example. Like there are many ways to implement a set, like with AVL trees or breadlike trees or any other tree. And with locales, you have to do this instantiation of the assumptions manually. So you have to, every function of the implementation that you assume, you have to provide an equivalent function and manually map them to one another and prove that they satisfy the local assumptions. The refinement framework is basically a way to automatically do that, to automate this process as much as possible. And it's, there is a theoretical, there's a theoretically interesting aspect of it where, for example, you could implement this refinement using so-called relational parametricity. I don't know if you know what that concept is, but basically it's a way to move theorems across different types. This is the theoretical background or the theoretical foundations of Peter Lamich's framework. Refinement framework is this, like something that moves theorems from one type to the other using relational parametricity. But so it basically replaces the manual instantiation of local assumptions by automation. That's what it does. I hope that answers your question.
Yeah, that was a very good response. I have another question.
Yeah.
You mentioned before that symmetry breaking is a problem in formalization.
Yeah.
Could you expand on that? I don't think I quite understood what you meant.
Okay, so let me just go there with an example. I will just show you an example that would make it easier for us. Okay, so here, for instance, if you want to here, if you remember, we found this odd cycle and then we contracted into this, right? Or we found an odd cycle. We don't know what, we know that U prime comes from an odd cycle. Like we know that some odd cycle was contracted into U prime. Now we want to show that there is an augmenting path in the original graph. So if you expand U prime into the original odd cycle, you want to show that there is an augmenting path in the original graph, right? So what is symmetry breaking here? For example, you don't know firstly if that augmenting path that you're trying to extract, does it go through the bottom of that odd cycle, or does it go through the upper part of the cycle? Because U8 could be connected to 7 or 6, and it doesn't make any difference in the proof. So they are symmetric goals. Like you basically want to construct an augmenting path for the unknown odd cycle that induced U prime, but you don't know what is the augmenting path, because the augmenting path could be connected to U7 or U6, and both cases you have to cover both cases in your proof, and they're exactly the same thing. It's just as they're symmetric, and this is what I mean by symmetries. Now, the way you do this with formalization, you just prove a general lemma. You try to come up with a general condition that characterizes both cases for U7 and U6. Like if you assume that U8 was connected to 7 versus 6, you try and come up with a general lemma that covers both cases, and this is how we handle symmetry breaking. But that should be done more automatically, because in other areas of AI and automated reasoning, like planning and set solving and even first order theorem proving, there are ways to handle such symmetries automatically without having to every time come up with a lemma that generalizes to all symmetric cases.
Yeah, thank you.
No worries.
I have a question.
Thanks. There's another question.
Yes. Hi, Mohammed. Thank you so much for your talk. Can you hear me? I was wondering, the first project that you mentioned, you said in the end that it turned out there were 18 invariants that you need to check for, but not all of them were in the original proof, right? So I was wondering, to what extent did the Isabelle formalization help in detecting this issue? Was it something that you saw, like maybe some finding tools or how did this emerge from your work?
Yeah, I mean, it's just like the usual story with this. Like, it just forces you to come up with the proof, not just forces you. But like, I can tell you specifically this story, but it's hard to, of course, derive from it a general pattern because it's anecdotal, right? So the way this originally was, like this was originally done, was the following. Like, so Kurt Melon had this proof, and he just assumed that those that we don't need the invariance in one direction at all, because it's an obvious step. He didn't know that it's complicated. But once you try and put that in a theorem prover, you actually find that there are many big gaps in this step, and it's not in any way obvious. That needed almost half, like an equal amount of theorems and lines of proof to the other part that he thought was non-trivial. So basically, he just didn't understand the proof, and that's what he even said. Like, he didn't fully understand the complexity of that side of it. And so when you transformalize it, it doesn't work out, and you gradually build up your understanding by fixing the problems in the formalization.
Thank you. It's quite interesting that the author had the correct intuition without checking all this that you mentioned. So
yeah, it's interesting. Yeah. I'm proud of this specific project a lot. Yeah.
Thank you.
No worries.